Happy learning! Today we're going to talk about the traveling salesman problem. Okay, so what is the traveling salesman problem? Well, basically, a salesman wants to visit a bunch of homes and wants to do it as cheaply as possible, right? They don't want to spend that much time traveling. And so how do we do that in graph theory is we want to find the shortest Hamiltonian cycle on a weighted complete graph. In general, this is hard to do, to find the shortest possible. And so what we're going to talk about today is some ways to get good, but maybe not the best Hamiltonian cycles. But in practice, good is usually good enough, hence the term good. All right, so we'll start by talking through an algorithm that will guarantee you to get the best possible Hamiltonian cycle. But unfortunately, this algorithm does not work in practice because it takes a computer too long to run. So what is that algorithm? It's called the brute force algorithm. Okay, and so what is the brute force algorithm? We're going to brute force all possible Hamiltonian cycles. So what is it? Find all n minus 1 factorial Hamiltonian cycles starting at a specific vertex. Okay, this algorithm is great if our number of vertices is small, but it's not practical if our number of vertices is like over 20. Okay, and so let's just do a very quick example with the brute force, and then we'll go on to some of the ones that you'd use in practice. Okay, so let's say this is our graph. And here are the weights. Okay, and we want to find the Hamiltonian cycle with least weight in this graph. And let's just say this will be our starting vertex for each of them. It doesn't really matter. Okay, so there are 6 routes that we have to choose from. So one of them is the following. And this has weight 3 plus 2 plus 15 plus 5. Okay, that is 25. If we do the same cycle but in reverse, it's going to have the same weight. Okay, so this is also 25. Another option is we go down, across, down, across. So that has weight 3 plus 12 plus 15 plus 8. That has weight 38. And same thing if we did it backwards or in reverse. Okay, so far these two are the winners. And let's try one more. Or I guess there's two more, but they pair up. if we start by going across and then diagonal. All right, and what is the weight of this one? 5 plus 12 plus 2 plus 8. That's 27. Okay, and then same thing with the last if we go backwards. All right, so either of these cycles would be the output of the brute force algorithm. But you can imagine if our number of vertices was large, this algorithm would just not be practical. Okay, so either of these cycles would be our output because it's the smallest of all these weights. Okay, I have in my notes, now this is from a few years ago, so computers have gotten a little bit better, but not much. If we had a graph with 26 vertices, it would take a supercomputer 200 years to complete this cycle. I don't have time for that, you know? So we need better options than relying on the brute force algorithm. All right, so the first kind of practical algorithm we're going to look at is the nearest neighbor algorithm. The nearest neighbor algorithm is we're at a vertex and we're going to travel to the nearest neighbor, provided that we don't close off the cycle too early. Okay, so pick a starting vertex. And travel to nearest neighbor. Okay, we just have to make sure we don't close off the cycle too early. Okay, so we do have to make sure we hit every single vertex. So there's going to be some times we're going to have to actually jump over one of the shortest edges and try a different one. Okay, I'm going to draw a complete graph with 5 vertices, but I'm going to actually represent it as a table. Okay, it's just going to be a little bit cleaner. You could imagine with all the edges, it's going to be hard to see what label goes to what. So we could actually represent our complete graphs with a table. And we're going to use this table for the rest of today's lesson. Okay, so how does it work? Well, we're going to have 5 vertices. And we really only care about the top part of it. These entries will tell us the weight of the edge between them. So there's no edge between A and A, so I just put a dash. But 325. So that tells us the AB edge has weight 325, 300, 125, and 100. This is symmetric, so I could put 325 here, but I'm not going to bother. BC has 315. BD is 375. And BE is 225. CD is 600. CE is 360. And DE is 305. All right, so this table actually captures all of the information of a weighted complete graph on 5 vertices. It's just a little bit easier to read than the graph is. All right, so let's apply nearest neighbor starting at A. All right, so let's draw our graph. And we'll say this is A. We are going to find the nearest neighbor to A. So that's all of these in this top row are A's neighbors. E is the nearest neighbor. Okay, what are E's neighbors? Well, here are the weights of E's neighbors. Again, we're going to pick the nearest neighbor, just making sure we don't go back to a vertex we've already seen. So 225. All right, now we're at B, and we need to find its nearest neighbors, or its nearest neighbor. We have to consider this option also. So that's one of the downsides of not writing out the entire table. But we're not going to travel back to A. We've already visited A. And we're not going to go to E because we just came from E. So it's one of these two. And so the smallest is, of course, C. Which is 315. All right, there's only one vertex that hasn't been visited yet, so we know that C is going to go to D. And that has a weight of 600. And now we're going to go back to the start. All right, so when we did nearest neighbor starting at A, we got a weight of 1,365, right? If we add up all of these numbers, we're going to get a total weight of 1,365. Okay? If we started at a different vertex, we might get a different cycle with a different weight. So our choice of vertex actually matters, a choice of starting vertex. And so one way to adjust for this is to do something called the repetitive nearest neighbor. All right, so repetitive nearest neighbor repetitive nearest neighbor works with, we're going to do the nearest neighbor algorithm for starting at each of the different vertices. Okay, so we would do it starting at A, then we would do it again starting at B, then do it again starting at C, and so forth until we get to every single vertex. So instead of doing it once, we would do it 5 times in this case. So we're going to apply the nearest neighbor algorithm n times, so then 5 times in this case. Once for each starting vertex. Okay, so if we were to apply this 5 times, we've already done it once starting at A. I'm going to show you what the outputs are if you start at B, C, D, and E, but you should obviously verify this on your own. So A we've already done. With B, so this would be B. It goes this way. So you can see it's actually the same. It's the same cycle as when we did A. So that has the same 1365 weight. If we did C, it would be slightly different. You'd get this cycle, which has a weight of 1600. If you do D, you would get the following. So these, right, A, B, C, and D, that's saying where we're starting our cycle. Like that's our first step. We'll find the nearest neighbor starting at D, and then go from there. It looks like this. Okay, this one should look familiar. It's that 1365 again. And if we start at E, we get this cycle, which has a weight of 1275. All right, so this cycle here would be the output of the repetitive nearest neighbor, because this has the least weight of all of them. Is this the best possible weight? No, it's not. There's actually a cycle that's a little bit smaller than 1275, but this is the best weight we get from repetitive nearest neighbor, so this would be our output. The best possible actually is 1270, so we got pretty close using a pretty easy to run algorithm. All right, so the next algorithm we're going to look at is called cheapest link. All right, and what is the cheapest link algorithm? It says instead of looking locally for the nearest neighbor, we're going to look globally for the smallest edge. Okay, so pick smallest available edge. Okay, but we have to be a little bit careful. We can't have a vertex with 3 edges coming out of it. So pick the smallest edge available so that no vertex has 3 highlighted edges incident to it. And no edge closes a cycle before hitting all the vertices. All right, so again, this is very simple. We look globally. What is the shortest edge? We're going to highlight that, include it in our cycle. And then we just have to be a little bit careful that we don't get something like this, right? You can't have this as part of a cycle. And then we also just have to make sure we don't close off the cycle too soon. All right, so let's apply this algorithm. Let's apply this algorithm to our example here. All right, and so we have our 5 vertices. All right, A, B, C, D, E. And at each step, we're going to find the shortest edge, the one of least weight. So AE, again, is going to be our first step. Okay, what's our next step? Again, we're going to find the edge with the least weight. That's AD. Okay, what's the edge with the least weight available? 225. BE. All right, what's next? AC is the next smallest. If we were to include AC, we got some problems here. If we include it, we would have 3 edges coming out of A, which we can't have, right? That's one of our conditions. So that no vertex has 3 highlighted edges incident to it. So if we included AC, we'd have some problems. So we're not going to use AC. What's the next smallest? DE. Okay, if we included DE, 3 edges out of E, that's a problem. Also, we would have a cycle. So we can't do that. Let's continue. What's the next smallest? BC. I like it. I like it a lot. All right, and now we could go through and check all of the remaining. I know that it's going to be CD because there's 1 edge left to include, and these guys still haven't been connected yet. So unfortunately, we have this 600 weight again. So total weight is 1365. Okay, and so in this case, we saw that repetitive nearest neighbor actually did a little bit better than cheapest link, but there are going to be some scenarios where cheapest link does better than repetitive nearest neighbor. And either way, these are not very complex. You could have a computer do this for very, very large completed graphs. Or complete graphs, sorry. There's one other algorithm we're going to talk about, but I'm going to make a special video for that one because it's a little bit trickier than these ones that we've looked at so far. So I'm going to finish today's video by talking about error. So the relative error for a solution is given by the following formula. So we use the Greek letter epsilon to represent our error. Not just because it looks like E, but epsilon, traditionally in mathematics, is used to represent a small quantity. So, we're being optimistic here that our errors are going to be small. All right, so what is the formula for relative error? It's the solution that we get minus the optimal value divided by optimal. All right, and so the only way we would know optimal is if we actually do the brute force algorithm. So in practice, we can't really get relative error every time. But in our example here, we can. So in our example, optimal was 1270. All right, so let's compute the relative error for the cheapest link and also for repetitive nearest neighbor. So repetitive nearest neighbor, epsilon is equal to our solution, 1275, minus 1270 over 1270. Okay, that is 0.39%. That is incredibly good. That's almost no error, all right? With cheapest link, we got a solution of 1365. So it's 1365 minus 1270 all over 1270. And we get an error of 7.48%. Okay, that's still pretty good, especially since it's not very computationally difficult to run either of these algorithms. Okay, so these are both pretty good algorithms for finding good, not perfect solutions to the traveling salesman problem. And like I said, I'm going to make one extra video to talk about the nearest insertion algorithm, which is good when you have a graph that's like gaining new vertices as the problem evolves. So for the real world, right? If you're trying to travel to a bunch of houses, sometimes new houses are built. So that's a good one when you're learning new information. Okay, well, I hope you enjoyed the video. I hope you like these algorithms. If you're into computer science, try to program these. They're easy enough to program, and they could help you solve some interesting problems. Okay, I'll see you next time. Bye-bye.